Hi, I'm Ben-Yaakov. This presentation is entitled Parallel Connection of Diodes. This is a second version of a video that I've taken off YouTube following a comment by one of the viewers. Here is the YouTube name of this viewer. And he commented that the original video lacked some information, which in fact I didn't put in because I thought it's going to complicate the presentation, but he is right, it should be put in. So this version includes this subject, which is the dependence of the saturation current of a diode on temperature. So here is the problem we are considering in this presentation. Sometimes we do need to parallel diodes in order to get higher current that one diode cannot carry. The basic model of a diode is presented by this equation. This is the diode current. This is the reverse saturation current. Voltage across the diode, constants. K is Boltzmann constant. T is degrees in Kelvin. And Q is the electron charge. So this is the equation. And we also know that the voltage across the diode for a constant current drops by about 2.5 millivolt per degree centigrade. This gives the feeling that if you connect two diodes and one of them has a different thermal cooling arrangement, that is, the thermal resistance, say, is larger, it'll get hot, temperature will increase, voltage will reduce, and perhaps it'll sort of capture the current and there will be a thermal runaway. So this is something we're going to explore here in this presentation, and I'm going to do that by simulation using LT-SPICE. To do that, we do need a model for the thermal part of the problem, and here is the classical equivalent circuit that represents a thermal conduction between power delivered to a system. This is the thermal resistance, ambient temperature, and this is the thermal capacity. Now in this circuit, this sort of emulates the thermal behavior by an equivalent electrical system in which R is thermal resistance, V voltage here, or the voltage drop on the thermal resistor is temperature, and the current here is in fact the thermal power fed to this network. So here is a very basic fundamental schematics in LT-SPICE of two diodes which are connected in parallel. These are current sources defined by the equation of the diode. Here I have rearranged it so that the temperature will be in centigrade rather than in Kelvin. So I've added here 223 and normalized it. 26 millivolt is the voltage or the value at 300 degree Kelvin. And so these are the diodes. Here are the thermal model for each of the diodes. This is the power dissipated by one diode, calculated by the product of the voltage across the diode and the current through it. Same thing goes for the other diode. And here, therefore, would be the temperature of one diode and the temperature of the other diode. So this is very basic. This circuit now is being fed from a voltage source with a 50 volt step through a 10 ohm resistor. So the current is approximately 5 amp. That's a little bit less because of the voltage drop on the diode. And here is what I'm getting. If everything is equal, temperature will be the same for the two diodes. The current will be the same for the two diodes. Everything is okay. However, if I change the thermal resistance so that one of them will be 10 centigrade per watt, the other one 8, I see that there is a deviation. And what we see here is this is temperature now, a temperature difference. And here there is a current difference between the two. Notice that the diode with the higher thermal resistance has a higher temperature, as you'd expect, but a lower current. It's kind of reversed. We'll talk about it a little bit later. Now, if I change the situation, like I'm increasing the thermal resistance, like this is 50 and this is 40 rather than 10 and 8, you see that there is a bigger spread here. and again, it's the same phenomena as before. Now, if I'm changing the current, then of course, again, for a given situation, higher current, higher temperature of the diode, but in all, it kind of looks similar. But apart from a difference in the thermal resistance, there's of course a difference in the diodes themselves. They are not necessarily matched exactly one to one, and in particular, there might be a difference in the reverse saturation current. Say if one is 2 nanoamp and one is 1 nanoamp, then again I'm going to see a difference similar to what we have seen before. This is the temperature difference. So why is it that the system kind of stabilizes? Well, at this point, we see that temperature is here in this expression at the denominator here, which means that the higher temperature, the lower the current. Here it is. The higher the temperature, the lower the current. So therefore, there is sort of a negative feedback here, which sort of stabilizes the system. And therefore, we don't see like a runaway, but it sort of stabilizes to a situation that will accommodate all the requirements of these relationship. But, and this is something that I'm adding to this version of the presentation, this current, this constant, you might say, is not constant, it's temperature dependent. And in fact, it's increasing with temperature. So therefore, this term here is actually giving negative feedback, but this is actually positive feedback, because as the temperature goes up, this saturation current goes up, the diode current goes up again, and in some cases you might face the problem of thermal runaway. Now, how much does this current increase? Well, there is a rule of thumb saying that the increase is about like doubling or tripling every 10 degrees. This is what you see. There is, of course, an expression from the semiconductor behavior, but I'm not going into a more complex description, but rather to use this approximation. So I'm going to use the fact that experience shows that the current is increasing like doubling every 10 degrees, so therefore the expression is like 2 to the power of temperature, this will be in centigrade, divided by 10, so every 10 degrees it's doubling, or tripling, again, depending on the device, it's depending on the material, and there is a spread here. So what I'm going to do, I'm actually going to look at a given diode. So here I'm measuring the reverse saturation current of this diode, it's a 200 volt 3 amp diode, by exposing it to 200 volt and sweeping the temperature. This is something you can do in LT-Spice. It's a global temperature that you are sweeping. So by this, I can get the current for each one of the temperature, and here is what I'm getting. The current at 0 degree centigrade is 0.23 nanoamp, and then it goes up, and the sweep is from 0 to 120 degrees, and the steps are 10 degrees. Well, approximately the differences are the same. Well, it's not exactly, but I think it's good enough for our approximation. And in fact, if I look here, this is now this equation, okay, that I've put up, and I found that 2.2 to the power of t over 10 sort of matches here. It kind of looks pretty much the same. So I'm going to use this as a measure of how the reverse saturation current is increasing with temperature. Okay, this is centigrade. Now, starting at 0.238 nanoamp at 0 degrees centigrade, and then it goes up by about equal steps in terms of multiplication. There's another behavior that I like to include in the model that I'm going to use, and here it is shown by the fact that the model shows VI curve like this. This is something that I've generated with the basic model. And here is the VI curve for this particular diode. What we see in particular is that the slope here is indicating a dynamic incremental resistance, which is about 15 milliohm. So therefore, I can actually add to the model 15 milliohm. This is now the diode. The equation of the diode is this part, the current source, but the dissipation includes now, this is the dissipation for the thermal part, includes the 15 milliamp. So this will be an improved model of the diode, including the internal or dynamic resistance or incremental resistance. Again, we have the same basic equation as before, current source dependent on this equation. Once I do that, you see that I'm getting now a better match. This is now the model, adjusted model. This is the diode. Again, I got here a larger spread. I'm not going to worry about it that much now because I think it's, in effect, it's actually making stabilization worse because it's a larger spread. So I'm going to live with it and go on with the simulation. We are now ready to complete the model, adding the two additions. One is the internal dynamic resistance, and the second one is the dependence of the reverse saturation current on temperature and the actually updated value. I've also switched from a voltage source to a current source because I've experienced some convergence problems with LT spice with the voltage source. So I went to a current source, which seems to be working okay. We have 5 amps, so presumably if there is a balancing between the two diodes, then it'll be half for each. Now I'm running first this model with the 20 degrees centigrade per watt for one diode and then 15 degrees centigrade for the other. And here is what I'm getting. The temperature is about 55 for the first one, and then it's 45 for the other one. And here are the two currents, pretty close, not too far apart. But notice that in this case, the temperature of the diode with the higher thermal resistance, here it is, this one here, T1, is having a current which is also higher. This is in contrast to what we had before. Here it is. When the temperature of one of the diodes was higher, its current was in fact lower. So this reversal of behavior can be attributed to the fact that we have now actually positive feedback, because with this temperature dependence, the higher the temperature, the higher the current, which is opposite the effect of this term here. So we are experiencing sort of a positive feedback, but as we can see, the system is still stable, the loop is stable, and the current are pretty much the same. On the other hand, if I'm going to move to a much higher thermal resistance, 50 and 40 for the two diodes, in this case we see that the system is just unable to stabilize, and in fact what we are getting here is the T2 temperature is actually 25 degrees, current is about 0, while all the current is now being passed by the other diode and the temperature goes up to 140 and up. So this is certainly a case of an unbalanced situation. So what we find is that when the thermal resistance is very high and there is a considerable difference between the two sides, and the system cannot accommodate this situation. So what can be done? A solution that is sometimes adopted in the industry is to add series resistors. The idea is to add, in fact, negative feedback, because as the current increases, say one side, voltage drop on the resistor increases and the voltage across the diode decreases, so this has the tendency of bringing the current back down, so it's a negative feedback effect. So to test this, I've added two resistors, pretty small ones, 100 milliohm for the same case here as we had before. And here it is. Lo and behold, these resistors indeed can stabilize the system. We see that the currents are pretty much the same. Temperature are not too far away. Well, the temperature are high because we have high thermal resistance, so therefore the temperatures are high. And the current, as we can see, are pretty close. Now the downside here, of course, that we have power dissipation in the resistors. In this particular case, I find that it's only 1.25 watts, so it could be acceptable depending, of course, on the power level of the system. Now, we can understand what is going on by looking at the actual voltage drop on the diode. What we see here that the resistors now causing a voltage difference between the diodes. And this, of course, helps to stabilize the system. And here I'm looking at the voltage across each of the diodes, and we see that there is a difference. Here it's 542 millivolt, and here it's 528, which is sort of helping to balance the current. Another possibility is to bring the temperature of the two diodes to be close or preferably the same. Well, you can never have the same temperature for the two diodes, even if they are on the same die, because there is always a temperature gradient. But if they are on the same die, or if they are two separate diodes, but they are placed on the same substrate, very close one to the other, so the temperature of the diode will be very close as compared to the temperature drop between the diode and the ambient. So to test this, what I did, I'm making the two temperature the same by actually connecting here. So the two diodes are dissipating power, and this is the power which is sort of heating it up, the assembly, but the temperature of the two diodes are the same. And what I'm getting here is that if indeed the temperature is the same, then the current is exactly the same. That makes sense, because if the temperature is the same, the current will be the same. But hold on, what happens if the diodes are not exactly the same? Well, you cannot expect the two diodes to be identical and match 100%. There's always be a difference. Now, obviously, if it's two diodes on the same die that pass the same process, then they'll be pretty close. But if these are two different diodes, then you'd expect a difference. So to test this, what I did, I've put here two different coefficients for the reverse saturation current. I've increased it a little bit, so we'll see a bigger difference. So everything is the same. We have the same temperature. The power dissipation is of this thing. This is just 1 microohm, doesn't do anything. So this is pretty much the same temperature, but the reverse saturation current is different by 50%. And what I'm getting here is that in this case, as you would expect, well, first of all, the temperature is the same because this is what I did, but there is now a difference. The difference, however, is not as much as you'd expect, because here there is a 50% 1 to 2 ratio, while here it's not 1 to 2, it's 1 to 1.5. Well, the reason is that I'm still having here the internal dynamic resistance, which is sort of helping a little bit the balance. So this is why the difference is not as big as the coefficients here. So what are the conclusions of this presentation? First of all, we see that there is sort of a self-balancing, a natural self-balancing of diode to some extent. And then the diode parameter spread is very important, more perhaps than the thermal resistance difference, which could be not that much. Also, we have seen that the external resistor indeed can balance the current, but of course it's the expense of extra power dissipation. And finally, which is perhaps very important coming out of this presentation, that simulation could be a very useful tool to study the paralleling problem. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.